so we had got to a stage where we were analyzing the green function for the wave equation, the ordinary wave equation, and we found a formula for the fundamental green function in d dimensions, which read something like g in d dimensions of r and tau was, if I recall right, it's there's a c theta of tau and then a 2 pi to the power d and then an integral d dk in k space e to the I k dot r sine c tau k over k. This was the general expression. After we did the integration over the frequency over omega, we are left with the integral over the wave vector k, and it is this expression here which you have to analyze, and we did this for d equal to 1 I believe, and d equal to 2 also. I mentioned it quickly just to run over what happened for d equal to 2. We chose plane polar coordinates with the x axis along the direction of the vector r, and then this becomes k dk, so that gets killed, and then we have g2 of r and tau equal to c theta of tau divided by 2 pi the whole squared, and then 0 to infinity dk, because the other k gets killed, sine c tau k, and then we have an integral 0 to 2 pi e to the I kr cos phi, which was a j0 of kr apart from a factor 2 pi, so that goes away, and then you have this j0 of kr in this fashion. And of course one way to do this integral is to write this as the imaginary part of 0 to infinity dk e to the I c tau k j0 of kr, and to regard this as the Laplace transform to s equal to minus I c tau of this function of the j0, and then we have already got earlier we had a formula for the Laplace transform of this of the j0, so we had 0 to infinity dk e to the minus sk j0 of kr is equal to 1 over the square root of s squared plus r squared. Okay. You can do that in many ways. You can expand this in a power series and do it term by term, because we know the Laplace transform of a power, and then recombine terms and it becomes this algebraic expression. Okay. So this thing here will give you 1 over square root of minus c squared tau squared plus r squared, and you take out the I, take the imaginary part, etc., and you end up with the result that g2 of r and tau equal to 0 if c squared tau squared is less than r squared, because it is a causal green function, and it is equal to apart from these factors, these other factors sitting around. So you have c theta of tau over 2 pi 1 over square root of c squared tau squared minus r squared greater than r squared. That is the causal green function. Okay. And it is a slowly decaying function, goes like 1 over t for very large values of t for any fixed spatial point. Okay. So that was a 2-dimensional green function, and the surprise here is that you start with a delta function pulse at t equal to 0 or tau equal to 0 at the origin at capital R equal to 0, and it passes by you your point wherever you are located, the field point, as a slowly decaying pulse after a retarded time. Okay. Now what happens in 3 dimensions? That is the one of maximum interest to us. So in 3 dimensions slightly different thing, a rather different thing happens, and let us see what goes on. So in 3D g3 of r and tau is c theta of tau over 2 pi whole cube, and then 0 to infinity this is a k squared dk out there, sine c tau k, and then this e to the I k dot r. The obvious thing to do is to choose spherical polar coordinates with the axial direction with the z direction along the vector r, and then this is just e to the I k r cos theta. So the phi integral will give you a 2 pi factor that sits here, 2 pi squared, and then you have to do an integral minus 1 to 1 d of cos theta in a very familiar, by now familiar maneuver, e to the I k r cos theta. This is going to be e to the I k r minus e to the minus I k r, that is 2i sin k r divided by I k r. So this whole thing becomes 2 sin k r divided by I k r in this fashion. I am not happy about the i's. This is a 2i out there, and the I cancels, yeah? Yeah, the k cancels as well. So there was already a sin c tau k over k, and then there is an extra k here. So all these k squared factors cancel, k factors cancel, the I cancels, and you are left with just this thing here. So this is equal to c tau theta divided by I am just trying to check that we have all our factors right. I am trying to make sure that we have all our factors right. This is a 2 pi to the d, so it was 2 pi cubed. One of them went away in the phi integration, and the other one gave us a 2 sin k r. So there is a 2 sitting there, and let us see. So this is 4 pi squared r. You just have to make sure that all our factors come out right. Yes, okay. An integral from 0 to infinity. Oh, by the way, so let us write, okay, dk, and then a 2 sin a sin b kind of thing, that is equal to cos k times c tau minus r minus cosine of k times c tau plus r. That is the integral. Okay. And the cosine is of course an even function. So I might as well write this as minus infinity to infinity and put a factor 2. So this is equal to 1/2 minus infinity to infinity of this guy. Okay. Now adding the sign will not do anything because that is an odd function. So if I do that, in both cases this immediately gives us the result, because it says G3 of r and tau is equal to, I am worried about a minus sign. Was it a minus here to start with right from the beginning? Should have had a minus sign. Was it a minus? Just check whether it was. We could go back and do the whole thing, but I believe there was a minus sign sitting here. There have been so many minus signs that I am a little bit at a loss. Is this all right? Cos A cos B plus sin A sin B, and this is minus sin A sin B, so that part is okay. There should have been a minus somewhere here. Is there a minus? Was there a minus sign? Okay. Yes? Was there a minus sign right from the beginning?
No.
It is not relevant. We can fix those factors later, but I want to make sure that we get all our things right. I just want to make sure that I just want to make sure that we get everything right, but okay, up to a minus sign we have to worry about this a little later, but let us see where it takes us. This is equal to c theta of tau divided by 8 pi squared r, and then this integral can also be written as minus infinity to infinity dk e to the power I k times c tau minus r, because the sign part of it is 0 by symmetry, minus e to the minus e to the I k c tau plus r in this fashion, and these are delta functions. As you know, these are delta functions, so this thing is equal to c theta of tau over, apart from a 2 pi factor, so this becomes 4 pi r, and then this is a delta of c tau minus r minus delta of c tau plus r in this fashion, and I can pull down a factor c, I can take out a factor c, this is 1 over c times the same guy, so that goes away and it is tau minus r over c minus delta of tau plus r over c. But you see, both tau and r are positive, so this thing never fires, this thing is 0, essentially 0, and you are left with a green function, causal green function, which is a pure delta function at, this is remember this is delta of t minus t prime minus mod r minus r prime over c. Okay. So the initial pulse at capital R equal to 0, there was a pulse here at R equal to 0, and wherever you are at any point at time, so if this thing was emitted at time t prime, it reaches it at time t prime plus mod r minus r prime over c. This is the point r prime, and this is the point r, and it is again a delta function pulse. So you have this magic that what starts off as a delta function remains a delta function out here, modulated of course by this factor here, so this is equal to theta of tau over 4 pi r. The reason I am unhappy with this thing here, the sign which we have to fix, is that if c equal to infinity, as c tends to infinity, oh yes, it is perfect, it is alright. As c tends to infinity, notice what happens. The operator you are talking about is 1 over c squared d2 over dt2 minus del squared. As c tends to infinity, this disappears and you essentially have minus del squared, but remember that if c tends to infinity, you have a pure delta function of t minus t prime, which was there in the initial equation for g as well. So you have precisely minus 1 over 4 pi r as the green function for the operator del squared. We have the operator minus del squared here, so you got a plus 1 over 4 pi r, so the signs are okay. This fact that the green function for the wave operator, the causal green function, goes over into the green function for the Laplacian is again not always guaranteed, but in 3 dimensions it happens. But the important thing is that unlike the 2-dimensional case or the 1-dimensional case, you again have a delta function signal, undistorted, a pure delta function once again at a retarded time. Okay. Now of course this implies that if you write down solutions of the wave equation, so let us go right back and write down solutions of the wave equation. So if you gave me the equation 1 over c squared d2 over dt2 minus del squared acting on a function of r and t equal to a given function of r and t, then the particular integral corresponding to the causal solution here would be f of r and t equal to integral d3 r prime in 3 dimensions, guy here, divided by 4 pi mod r minus r prime, and then there is an integral over t, but the point is t must be set equal to t prime plus mod r minus r prime over c because of the delta function. So essentially you get g of r prime t prime where t prime stands for t plus mod r minus r prime over c. This is the retarded solution. So the source at an earlier time at t prime such that t prime is t plus this. So if you are looking for the solution at time t, then you must have started at an earlier time t equal to t prime minus mod r minus r prime over c, and that is what plays a role in the signal at time t, which is exactly what you expect of a retarded solution. So this is a causal retarded solution. And you are familiar with this in the context of say electrodynamics or something like that, where if you work in the Lorentz gauge, we know that in the Lorentz gauge both the scalar potential as well as the vector potential obey the wave equation, and then you can write down formal solutions to it in terms of for the retarded solutions, and that is a very straightforward matter now, because if you recall the equation satisfied by the scalar potential is 1 over c squared d2 over dt2 minus del squared phi of r and t equal to the charge density epsilon naught in this fashion in the Lorentz gauge. Where you have 1 over c squared d phi over dt plus del dot A equal to 0 in that gauge. In this gauge you have the wave equation with the source term being the scalar being the charge density for the scalar potential, and the same thing acts on the vector potential A of r comma t equal to, out here you have mu naught j of r comma t. You can write this for each Cartesian component of A, and then you have a set of wave equations, and the formal solutions to these equations, which are causal and retarded, are given by this on this side, where G is respectively either rho over epsilon naught or mu naught G, each Cartesian component. And then of course after that you have the task still of finding the electric and magnetic fields. So you still need to write down after you solve for phi and A, you still have to find E, which is minus delta A over delta T minus grad phi, as you know, and B of course is curl A. So in principle, once you have the retarded solution, you can compute now what the E and B are at any space-time point given the sources rho and G. Now you also know that the Lorentz gauge happens to be Lorentz invariant, namely if you are in the Lorentz gauge in one frame of reference, you are in the Lorentz gauge in all frames of reference automatically, because this condition here is really a 4-dimensional divergence. So this is really del mu A mu equal to 0, where this is the 4-vector potential whose time component is phi over c and space components are the 3 vectors A. Okay. So this is a one way of deriving these retarded solutions explicitly. It is still an exercise which you must undertake to find, to put this in and then find that curl, find the curl and the divergence and the derivative, etc. Okay. Not altogether trivial, because remember that sitting inside here there is an R dependence out here which will get differentiated. So you have to be a little careful, and that is how you get the correct retarded solutions. Okay. So that is an exercise in electromagnetism which I am sure is a standard exercise. Yeah.
What does it mean to modulate the delta function?
Pardon me?
There is a 1 by r dependence on the delta function, right, as a function of time.
Yes.
So what does that mean? Does the area underneath the curve?
No, the 1 by r is always there because there is a del squared sitting there. So this is really a reflection of that. but the fact is in 3 dimensions the t is replaced, just replaced by t prime plus mod r minus r prime over c exactly. That is the crucial point, that this solution is over a specific time out here. This t prime stands for t minus mod r minus r prime over c. Okay. And then this 1 over r will always be there whenever you have a Laplacian. It is in 3 dimensions you expect a thing of this kind, right, because you expect the effect to be decreased as r increases. This whole thing is the inverse square kind of thing, right. So that is really what this reflects, but the crucial point is this, that it is undistorted, unlike 2 dimensions or 1 dimension where a delta function impulse does not come to any other point as a delta function impulse. Okay. Now the question is, what happens in higher dimensions? I can mathematically look at it and ask, what do I do about the Green function in an arbitrary dimensionality, d greater than or equal to 4 for instance? Well, that requires a little bit of effort, but there is an interesting way of doing this problem, and that requires relativistic invariance. That is, if you for the moment say that c is the speed of light in vacuum and the wave operator corresponds to light propagation for instance, then this operator, as you know, del squared, this is really the so called box operator in 4 dimensions, right, which is the 4 dimensional, the D'Alembertian or the analog of the Laplacian in 3 dimensions. Okay. It is relativistically invariant. In other words, this equation, if f and g are scalars, is invariant under Lorentz transformations, not just under rotations completely. Then we can say a lot more, because it turns out then that the proper quantity to look at is this invariant quantity, c squared t squared minus r squared is the interval between the origin in space time and any point with space time coordinates t and r, t and the components of r. So if you call this quantity s squared equal to this, then this Green function can be written down by looking at the fact that it is really s squared that appears everywhere. You saw that in 2 dimensions we had 1 over square root of this s squared essentially, and you also know that for s squared less than 0 this Green function must be 0 by causality, because I said it generally ends up being 0 for c squared tau squared less than r squared. So in terms of the light cone, which you are probably familiar with, so if you plot a space axis here and the time axis here, then the 45-degree line, this is how light would propagate in this direction. I flash a beam of light, this world line is this thing here. Everything here is the future for this person, everything here is the past, and these are elsewhere and elsewhen because they are space like separated. Okay. No causal signal can can communicate between this point and this or this or this. No causal signal can occur, right. So for instance, if this person throws a ball at this person and he catches it, the speed of this ball is less than the speed of light, so this thing will have a slope which is lower than this and will go along a path like this, and this person will catch it after he gets a little older. So right now so this thing here, by the way, if I pretend that there are 2 more directions here for the space, this is really a cone. This is the famous light cone, and what we are saying is that this region corresponds to c squared tau squared greater than r squared, and here it is less than r squared, and here it is greater than r squared inside. That is the region where the Green function is not 0 and 2 points which are separated by a time like interval can communicate with each other causally. 2 points with space like separation cannot communicate with each other. Okay. So these Green functions we are talking about are identically 0 in these regions outside these light cones, and inside it has got some value out here. Now one can use this relativistic invariance to actually solve this problem, because when you have time like separation, when you have a vector which is time like, so you have a 4-dimensional vector, let me call it A, this is equal to some A0, A1, A2, A3, and these 3 are what you normally combine into this thing A, then the dot product of this vector with itself is A0 squared minus A vector squared, this quantity here. When it is positive, you say it is a time like vector. when it is negative it is a space like vector, and when it is 0 you say it is a light like vector, because for light see t equal to r directly. Now it turns out that when you have a time like vector you can always make a Lorentz transformation to another frame of reference, another inertial frame, such that in the transformed frame you have only the time component and all these components are 0. In other words, you can make the interval purely time like, no space component at all. That is always possible. So you can always go to another frame of reference where this vector will look like this, will go to some a prime which is equal to a naught prime and 0 0 0. You can always do this. And there is a practical, let me come back and tell you, you actually do this all the time when you look at material particles. You go to what is called a rest frame of this particle. In the rest frame the linear momentum is 0 and there is only an energy, a rest energy of this particle. On the other hand, when the vector is space like, when this sign of this quantity is negative, then it means that a vector like this is space like, this point here is that space like interval. In such a case you can always go to a Lorentz frame such that you have simultaneity, such that this separation has 0 separation in the time coordinate but is purely space like. You can always do this for space like particles, space like intervals. Okay. Now our green functions are 0 outside and non-zero inside, and you can always go to a frame where this interval s square root of s squared if you like can be made to have only a time component. Okay. Then the matter becomes very simple and you end up with the following result. You end up with a result that g in d dimensions really a function of this variable s squared if you like. This thing here becomes proportional to, I just write the result down, a derivative of a delta function of s squared at s squared equal to 0, that is c squared t squared tau squared minus capital R squared if you like. So let us stick to that notation, c squared tau squared minus R squared. So it is the derivative of this delta function. This is a scalar quantity, so it is a single one dimensional delta function, but the derivative is very strange. It is ds to the power d minus 3 over 2. It is what is called a fractional derivative of the delta function. Now how do you define this? Well, how do you define a delta function? You define it by multiplying by some function and then integrating and giving a rule for this integration. Similarly, derivatives of delta functions, you are supposed to do integration by parts so that the derivatives act on the function, the test function, and a fractional derivative is defined via its Fourier transform. And it turns out that, well, it is obvious from here that when you can give meaning to this for all values of d, both even and odd. When d is an odd number, when d is an odd integer, odd number of dimensions, then d minus 3 is an even number, divides 2, so you get a derivative, you get an actual derivative of some order, some integer order of the delta function. So this will be a pulse once again, and notice that in d equal to 3 it is the delta function itself, that is it. That is why in d equal to 3 you got a pure delta function as the answer. In d equal to 5 you will get the first derivative of a delta function. Now what does the first derivative of a delta function look like? It is more singular than the delta function. I mean, just very roughly heuristically you can see that if this is your delta function, so imagine approximating it by a very steep function, the origin. If I differentiate such a function, I am going to get something like this. It is going to be very singular in the limit, more singular than the delta function. Roughly speaking, delta prime of x is like delta of x over minus x. The second derivative is even more singular and so on. So for all odd values of d out here, for higher dimensionalities, you can see that you get singular objects. They are pulses, but they are not the original delta function pulse, they are like derivatives of this delta function. On the other hand, if it is an even value, d is an even value, like for instance d equal to 4 for instance, then you get a half derivative of this fellow here. What this means is that it is really an integral of some kind. It is an integral transform. You can write this delta function, a fractional derivative, as an integral transform, and then it is an extended function. We saw already that d equal to 2 we had an extended function 1 over square root of this s squared, and that is what happens in all the even number of dimensions. So this single formula can be derived using the relativistic invariance of this problem, and it tells you in a very compact way what the green function is in all cases here. There is another relation which you can establish which is also very interesting, and it says G at dimension d plus 2 is minus 1 over 2 pi d, a second derivative of G of d. So where S so if you give me the green function in dimension d, I generate for you the green function in dimension d plus 2, etc. These relations can be proved using this invariance, relativistic invariance. I will not go further into this except to point out that mathematically you can solve this problem for every dimensionality. Yes. And this relativistic invariance is a clever trick to find this, find these green functions. Okay. Now let us turn to a slightly more complicated problem than the wavy equation, and this is the operator which you get in quantum mechanics when you do relativistic quantum mechanics of a particle. Okay. I am not sure if you are already familiar with relativistic quantum mechanics, the Klein-Gordon equation for a scalar particle. Well, since not all of you may be familiar with it, let me do this in an extremely simple way and at least motivate where this equation comes from. We know that if you have a relativistic particle, then the energy and momentum of a free particle are related by the following equation: E squared over c squared minus the linear momentum squared is equal to m squared c squared, where this fellow here is called the rest mass of the particle. That is the energy momentum relation for a free particle, relativistic free particle. Okay. Now this quantity E over c comma p is a 4 vector, a 4-dimensional vector, and you can see now that what we have got here is the analog of s squared. We square the time component and we subtract the square of the spatial components, and you get the dot product of the vector with itself. So this implies that p mu is E over c minus p, and p dot p is p mu summed over this mu values 0, 1, 2, 3. This is precisely E squared over c squared minus p vector squared, and that is equal to this. This quantity for real m, real masses, positive masses, is greater than 0. So this means that a physical particle of non-zero rest mass, positive rest mass, its energy momentum 4 vector is a time-like 4 vector, which means you can always go to a frame of reference in which its components are such that the space components are all 0 and there is only a time component. So you can always go to a frame of reference in which this particle, the p mu, goes to prime equal to whatever its value is when the momentum is 0, and you can see that E squared is m squared c4, so E is mc squared, so you have mc squared and 0, 0, 0. Okay. That is what you call the rest frame of a particle, right? Because it is at rest, but it has a non-zero energy, the rest energy, and when it is moving, it moves on a hyperboloid, because if I plot say the x component of the momentum p versus E here, and the y and z come out, you need more dimensions for it, then you can see that this line is E equal to Cp, this case, and this is E equal to minus Cp on the other side. That is the light cone. And what does a physical particle's relation look like? This thing here, if I plot E versus P, it looks like this. It is really a hyperboloid of revolution, and this quantity here is precisely mc squared, right? That is the rest energy, but when it is moving, it is on this hyperboloid, it is called the mass shell. it stays on this hyperboloid as long as it is a free particle. If you put a potential, then it changes, the energy momentum relation may change. But this thing here is for a physical particle here. Light would travel along this or that, this on the light cone, okay, and there are no physical particles which correspond to a vector here or here at this place, okay. Anyway, to get back to this, when you introduce quantum mechanics, what you do essentially is to change to wave functions. You say, look, I do not have things like momentum and position and so on for these particles, I have some wave function which describes this particle, and then on this wave function these quantities, energy, momentum, etc., are replaced by operators. They act on this wave function, and depending on what basis you choose, the representation of these operators is different depending on the representation. But you know that this is essentially the Hamiltonian operator, and we know that crudely speaking the correspondence is E is replaced by this when it acts on wave functions, and P is replaced by minus IH cross gradient when it acts on position space wave functions. That is the prescription, right. Now put that in here and see what happens. This says that if you have a particle whose wave function is represented by phi of r comma t, then this thing here is minus h cross squared d2 over dt2 over c squared, because I put in E squared acting on that wave function, I end up with a second derivative, and this is minus p squared. So this is equal to plus h cross squared del squared acting on this, is equal to m squared c squared acting on phi. So that must be the relativistic wave equation obeyed by a particle whose wave function is phi of r comma t in the case when it has no internal degrees of freedom, so no spin or any complication like that. But let us rewrite this equation, and what do you get? You get 1 over c squared d2 over dt2. I divide through by h cross squared, so let us get rid of this. And then I change the signs, so there is a minus here and there is a minus here, so it is minus del squared plus m squared c squared over h cross squared phi equal to 0. Okay. Now what is this quantity here? We can readily identify this quantity. H over mc, mc is the Compton momentum, h cross over mc is like the Compton wavelength, right. So this fellow says that out here this has dimensions of 1 over length squared, so does this 1 over length squared, and this is 1 over the Compton wavelength squared. So let us give this some name, let us call this mu or something like that, mu squared, okay. And then you have this equation which is 1 over c squared d2 over dt2 minus del squared plus mu squared on phi equal to 0. This equation is called the Klein-Gordon equation. It goes one beyond the wave equation and gives you an extra term out here, okay. Now of course this portion alone is the box operator, so really what you have is box plus mu squared phi equal to 0 in this case. Now in the case of a photon, in the case of electromagnetism, in the Lorentz gauge, when you have del mu a mu equal to 0, then the rest mass of a photon is 0 out here, and sure enough we know that for photons when mu equal to 0 you have box, and then you have a mu equal to 0. This is a different mu, by the way, I am sorry to use this, but this is the 4 vector potential. I am again sorry to use this phi, I should have used some other function here. Let us call this wave function psi, because that is more traditional. Psi. I use phi because phi is very often used for a scalar field with no spin, so that's, and psi is used for spinners and so on. So anyway, so this is the scalar potential in electromagnetism and A, the free vector potential, and together Maxwell's equations satisfy this in the absence of sources. What happens if you put in sources? Suppose you have, just for reference so that we know what we are talking about, you take C times rho and the current density, and together these constitute a 4-dimensional vector called the 4 current density. They transform under Lorentz transformations like a 4 vector. Now what does this equation become when you have a vector, when you have these sources, when they are non-zero? Well, obviously that is the left hand side is a 4 vectors, the right hand side must be a 4 vector and must be depend on the sources, the only one is J mu. So it is clear this is equal to J mu. Okay. And just to be sure that we have the same normalization there, it is equal to mu naught J mu. Not J mu. Okay. In those units. But that is the inhomogeneous equation. This is the homogeneous equation in the absence of sources. Pure radiation field, for example, will satisfy this equal to 0 in the Lorentz gauge, and they describe electromagnetic waves. Okay. But you have the problem of solving the Klein-Gordon equation as well. So let us see what happens in the more general case. Suppose you have again some function of r and t equal to a given function of r and t, and we would like to write down the green function for this operator. Once again, what would you do? You do exactly the same thing as before, take a Fourier transform with space and time, and then you get g tilde of k vector and omega. Let us do this in 3 dimensions. You can do this in any number of dimensions, but let us write it down in 3 dimensions. What is going to happen? It will be more or less the same as before, except that this fellow here would satisfy the following equation. If I do a Fourier transform with respect to time, I pick up a minus omega squared over c squared for this fellow. Here it is a minus k squared, so this becomes a plus k squared plus mu squared on this, and that must be equal to 1, the Fourier transform of a delta function. So this will imply that in this case g tilde of k and omega equal to minus c squared over omega squared minus k squared plus mu squared. Earlier you had just k squared, now you got k squared plus mu squared here. So we play the same game as before, we do the integration etc., and then you are left with picking up poles. So you will end up with, wherever k appeared, you are going to have square root of k squared plus mu squared appearing. So this will mean that this g of 3 dimensions, for example, but you can actually write it down in d dimensions, why not? So d of r and tau in this case is equal to, apart from this factor c squared or whatever comes out, c an integral d dk, usual 2 pi to the d factor here, e to the I k dot r, which will still be sitting there, and then you get a sine c, not c yeah, sine c tau, not k, but you would get omega sub k divided by omega sub k plus this. Okay. So that is all that will happen when you pick up these poles. Instead of the poles at plus or minus ck, it occurs at square root of k squared plus omega mu squared on both sides. So you have to do this integral, which of course is considerably more complicated than doing the integral with just k here. You had k, then this became a little relatively easy, especially the fact that factors of k cancelled again the k to the d minus 1 here in 2 and 3 dimensions etc. They made life very easy, but now you are stuck with this, you have to do this. Well, you can do it, there are various kinds of Bessel functions, the Neumann functions and so on, but the reason I brought this up was because once you do the wave operator you can also do the Klein-Gordon operator in this case and formally write the solution down, although it is not so trivial to write it down here. You can again ask for the causal green function, write this and write the expression down explicitly. So the earlier case with just the wave operator would apply for instance to light, but this would apply or in this language to zero rest mass particles. But the more general case where you have a non-zero mu squared also comes within this family of hyperbolic equations, and you can solve it pretty much the same way in this case. There are many other interesting things that happen which I do not want to get into here. For instance, this quantity d3k is not relativistically invariant because there is length contraction. So this will contract. The 4-dimensional volume element is invariant under Lorentz transformations, but this quantity is not. However, d3k divided by omega k is Lorentz invariant once again, etc. So you can use this fact. You can again, it is a very powerful statement. Just as I showed you that the general d-dimensional thing could be written down using Lorentz invariance of this operator, you can do similar things. By the way, this is also a scalar operator under Lorentz transformations. This quantity here is invariant. So one can use this fact in writing down the green functions. Not much interest in actually writing this down explicitly, except if you want to solve the problem explicitly, but all the properties that you need of this green function can be read out from the integral representation itself.